You know that feeling when you're faced with a really tough choice? You're trying to get the absolute best outcome, but you've got limited time or money or resources. We've all been there. Well, what if I told you there's an entire field of science dedicated to solving that exact problem?
It's the classic dilemma, right? It doesn't matter if you're running a business, planning a big project, or even just figuring out what to grow on a farm. You've got limits, but you want to maximize your success. So how in the world do you find that one single perfect answer?
Well, that's where operations research, or just OR for short, comes in. It's a seriously powerful tool that uses math and logic to help us make the very best decisions. You can think of it like a blueprint for making the optimal choice, especially when things get complicated.
So, how does this actually work? Well, here's our game plan. First, we're going to unpack the science behind making these decisions. Then, we'll roll up our sleeves and model a real-world problem. We'll turn that problem into a profit equation, lay down the rules of the game, and then, the really exciting part, we'll find that one optimal answer. And finally, we'll zoom out and see why this kind of math matters in so many ways you probably haven't even thought of.
All right, first up, the science of best decisions. You see, operations research isn't just about crunching random numbers. It's a really clear, structured process, a blueprint that turns messy, real-world problems into something clear that we can actually solve.
And here is that very blueprint. It always starts with step 1. You have to clearly define the problem. Makes sense, right? You can't solve what you don't understand. But the real magic, the absolute heart of OR, is step 2, constructing a model. This is where we take a complicated real-world situation and translate it into the clean, precise language of mathematics. After that, it's all about gathering the data, finding a solution, testing it, and finally, using those results to make a real impact.
So, to make this all feel a bit more real, let's walk through a classic example, a farmer's dilemma. Our farmer needs to figure out what to plant to make the most money, and we are going to use operations research to find the perfect answer.
Okay, so here's the situation. The farmer can plant either corn or wheat. As you can see, each one has a different cost to plant, a different yield, and a different profit. But that's not all. The farmer also has some hard limits. Only 100 acres of land, a budget of $15,000, and only enough storage for 4,000 bushels of grain. All this data, this is the raw material for our mathematical model.
Now for the really fun part, turning all of this into math. The very first step when you build any model is to figure out the goal. So, what does our farmer really want? Simple, maximum profit.
In the world of OR, we call this goal the objective function. Our objective here is to maximize the profit, which we'll just represent with the letter P. This is the number we want to make as big as it can possibly be.
Now, to figure out that profit, we need to know what the farmer can actually control. We call these the decision variables. Let's just say X is the number of acres of corn the farmer plants, and Y is the number of acres of wheat. These are the two levers the farmer can actually pull to change the outcome.
Okay, so where in the world does this equation come from? Let's break it down. We know the total profit, P, is just the profit from the corn plus the profit from the wheat. So let's look at corn first. Our data says that for every acre of corn, that's our X, the farmer gets 110 bushels, and each one of those bushels earns a profit of $1.30. So you just multiply them. 110 times 1.30 gives you $143 of profit for every single acre of corn. That's our 143X. Now for wheat, our Y. Each acre of wheat gives 30 bushels, and each bushel earns $2. 30 times 2 is $60 of profit per acre of wheat, and that's our 60Y. Put it all together, and our total profit is 143 times the acres of corn plus 60 times the acres of wheat, and that right there is our objective function.
But, of course, the farmer can't just plant 1,000,000 acres of corn to get infinite profit. This is where those real-world limits come into play. In operations research, we call these the constraints. They're basically the rules of the game.
First up, the land. The number of corn acres, X, plus the number of wheat acres, Y, has to be less than or equal to the 100 acres the farmer actually has. Now let's look at that symbol, less than or equal to. It's called less than or equal to. That little line underneath the less than sign is super important. It means the total can be exactly 100, but it can't be even a tiny bit more. This one simple inequality perfectly captures that real-world limit.
Next up, the money. It costs $120 for each acre of corn. that's 120x, and 210 for each acre of wheat, or 210y. The total of those costs has to be, you guessed it, less than or equal to the farmer's $15,000 budget. It's just another rule translated into another mathematical inequality.
And finally, we've got storage. The total bushels of corn, which is 110 times x, plus the total bushels of wheat, 30 times y, has to be less than or equal to that 4,000 bushel limit in the silo. You see what we're doing here? With every single constraint, we're mathematically building a fence around all the possible solutions. Now, there's one more rule. It's kind of a hidden one that's just pure common sense. The number of acres you plant, x and y, can't be negative. I mean, you can't plant negative 10 acres of corn, right? In math, we write this with the greater than or equal to symbol. Greater than or equal to. It just means x and y can be 0, or they can be any positive number. It seems obvious, but for a mathematical model to work, every single rule has to be stated out loud.
Okay, let's just pause for a second and see what we've done. We've built a complete mathematical model of the farmer's problem. We have our goal, maximize profit, and we have all our rules, our constraints that we have to play by. So the big question is, how do we find the single best answer?
Well, because we only have two variables we're juggling, x and y, we can actually draw this problem on a graph. Each of our rules, our constraints, creates a line, and when you plot all those lines, they fence in a specific area on the graph. This area represents every single possible combination of corn and wheat the farmer could plant without breaking any rules. We call it the feasible region. Now, here's the amazing part. There's a fundamental theorem in this field that tells us something incredible. The best possible answer, the one that gives us the absolute maximum profit, will always be found at one of the corners of this shaded region. We don't have to check a million points inside, just the corners.
So that's what we do. We take our profit equation, P equals 143x plus 60y, and we plug in the values from each of those corner points. And when the dust settles, one corner stands out, giving us a maximum possible profit of $6,460. But a number is just a number. What does that actually mean for our farmer?
Well, it tells the farmer exactly what to do. That profit of $6,460 comes from one specific mix, planting 20 acres of corn and 60 acres of wheat. This isn't just a good guess. It is the mathematically proven, single best solution to the farmer's problem.
Now that is a fantastic solution for our farmer. But why should the rest of us care about this kind of math? Well, because the exact same logic that optimized this small farm is being used right now to optimize massive, incredibly complex systems all over the world.
I mean, just think about it. Instead of acres of corn and wheat, imagine a company trying to decide on its product mix. Instead of land and capital, they have machine hours and a budget. OR is the science behind deciding how much stock to reorder, creating the most efficient delivery schedules, managing billion-dollar investment portfolios, and even figuring out the best work shifts for a hospital. It is absolutely everywhere. This quote from the UK's Operational Research Society just captures the scale of it all so perfectly. This is about using the scientific method to tackle the huge, complicated systems that run our modern world. Our systems of people, machines, materials, and money.
So, the next time you see a delivery truck following a very specific route, or you notice a store seems to have just the right amount of everything in stock, you can bet there's some of this math working behind the scenes. It really makes you wonder, doesn't it? What other hidden systems all around us are just waiting for the right model to be optimized?